Okay, everyone, I think we're going to start because we are tight on time today. Welcome to Modeling and Monitoring Challenges to Maritime Safety in the Arctic. This is part 2. Welcome to those that were here yesterday. To those that were not here yesterday, we focused more on logistics and risk management. Today, we're going to focus more on observations and product development. We're going to structure today as the 20-minute keynote speaker, 5 10-minute speakers, and then we're going to have a panel discussion. If we have time, there is a timer here for speakers, so you can track how much time you have left. Also, Penny, my colleague, will be holding up signs for if you are running out of time. So without further ado, I think we'll welcome our first speaker, Michiel Laarmers. He's an associate professor at Wageningen University in the Netherlands, and he'll be talking about new sea ice information and users and producers. So,
Yes. Is it on? I think so. Yeah. So thank you. It is a pleasure to be here in Tromsø, and it is a pleasure to be talking about let's say some of the work we have been doing over the last couple of years in the context of a research project, the Salient Seas project, but also in the context of my role as a co-chair of the Polar Prediction Project's Social and Economic Research Applications Group. So you could say, as you can hear, I'm a social scientist interested in the use and in the production of services in the European Arctic region. So this topic is called Mind the Gap. So maybe I should first explain what the gap is. In this case, it is what we call the usability gap. So it's basically the idea that yes, we can observe, yes, we can model, we can produce services on the basis of that, but often there is still a gap, or there is still, let's say, there's still work to be done to make sure that these services are actually used by users. And this is also sometimes called the last mile, right? So this idea of the last mile is increasingly used, whereby it is indicated that also in the logistics world, for example, it's relatively easy to get stuff to the warehouse, but this last mile of getting products, let's say, to the consumers is actually the hardest, the hardest part. So that is what this refers to. So I mentioned already the Salient Seas project. This was a project that has finished. We have done. I was the leader of that project. It was a project in which actually several Met services like Met Norway and DMI work together along with social science, social scientists, on producing new sea ice services and Met ocean services for all kinds of shipping sectors in the European Arctic. And we were, as you can see here in the slide, mostly focusing on cruise tourism, on expedition cruise tourism, on the fisheries, but also on hunters and traditional hunters and fishing activities in Greenland, etc., and also on ice breaking. And it's actually nice to see that one of our stakeholder advisors is in the back of the room there. And this was a project funded through the ERA4CS program, like a European call for co-producing services, let's say climate services in Europe. So we managed to get a project funded through that in that way to co-produce. That was really the idea. Let's say these services. We took an iterative approach, in the sense that we started by making contact with our end users in trying to understand what they need, what they experience, what kind of improvements they see. We did all kinds of, you could say, innovative, let's say, social science methodologies in order to dig deeper And with that, I mean to try to understand these user needs much more in context. So we did, for example, what is called a maptionnaire, so a survey basically of user needs, like say in context, so related to the spatial and the temporal, let's say, dimensions, for example, in which these users are experiencing certain conditions and certain problems. With all kinds of mapping exercises, scenario exercises, etc. We developed also, innovative, let's say, forecast, let's say CI's forecast, sub-seasonal to seasonal forecasts, and also wanted to understand how these are used, for example, and what kind of effect that these forecasts would make on these end users. On the basis of that project, a range of different demonstration services were developed. It says here climate services, but they're also, not only climate, I would say. So it's also really in the now casting. So these CI services that I already mentioned, but also climatologies of icebergs, for example. And also iceberg detection, let's say, tools. And it was during COVID, as you see in this picture. So a lot of the activity of contacting, of interacting with end users on these products, we did it before COVID in workshop settings. Very valuable that we were able to do that, but also partly during COVID through online meetings. And maybe to take out one of these approaches, we also tested these sub-seasonal to seasonal products through serious gaming. So that was a new approach in which we developed, basically, as you see in the picture here on the top left, on the basis of these products, we developed on the top right a serious game in which we kind of exposed end users, and in this case shipping captains and also planners of activities in the maritime Arctic, with a range of decision scenarios in which these products can make a difference or can play a role in order to find out how they relate to these products, how do they understand these products, and what kind of difference does it make in their decision making, in their confidence, and in the trust that they have in taking decisions on the ship, but also on the shore. So that's a bit of context that you know where we come from in this project. But I wanted to actually spend a little bit more time as part of this keynote talking about a final bit of research that we did that is really focused on this last mile idea, on this idea like we have these products, new products are being developed by the day, but how are they used and what are the kind of barriers that are preventing users to be using, let's say, all kinds of new types of services. And well, as a key question in there is also kind of like how to build trust, right? And how to foster trust in these usability, in overcoming this usability gap. As you see, also the literature, this is a well-known phenomenon. So I was already mentioning this idea of the last mile being implemented in these type of contexts, but also much earlier in the context of climate services. Understanding this usability gap has been identified already with a range of different, let's say, factors around fit, around interplay, around interaction that should be taken into account in order to make sure that products are taken up. And as you can see, like a trust is a very important one. But also, fit, also quality, and making sure that products fit the actual, let's say, decision context of users is really important. We wanted to build on trust in this study, and we used a conceptual framework by Mickler et al. In which they were looking at trust in smart products. And we added also a couple of elements there, like we added the element of peer endorsement. So the idea, do do colleagues in the field, in the shipping sector, are they already using? Are they recommending these type of products? So that's as an important extra factor. Like along with issues like a control, so. Around performance of the product, around the brand. Is it a well-known supplier, so to say, of these products? About onboarding, so what are the possibility to try out, to trial, or to play a role in order to build understanding of a certain product? Around handling, is it easy to use, etc. And also transparency. So a wide range of issues that all come into the picture there of building trust. And what we did was is a survey in order to understand, because as you can understand, there is a value chain involved here, and we wanted to understand some of the how do you say that, some of the conceptions of differences between providers and users around a number of different issues around trust. So we sometimes heard, let's say messages back and forth, like they do not understand what we need, or they, like the users, they do not understand our product, etc. So we thought this is an interesting, let's say, way of finding out like how substantive actually these barriers between these different groups are. And we did a cultural consensus analysis, in the sense that what that basically means is in groups there is often a shared understanding of an issue, right? And we wanted to see if we could kind of map, if we could measure the shared understanding of new product uptake in this mid-ocean Arctic field. So we did an online survey related to this, and maybe I should also say something about how this cultural consensus analysis work is basically based on the range of a range of statements, a range of true-false statements that a group of users and providers, let's say, answers, in which we could calculate on the basis of the whole group of respondents whether there was agreement on these statements, or let's say overall, but also look at how individual respondents then relate to this overall outcome of this group. So we could kind of test not only whether people agree or disagree, but also whether there is in that group a consensus around these issues. That is the interesting part, and not only for the whole group, but also for these two subgroups of providers and users in this case. It was a list of 33 questions, like true or false statements. We had it's a relatively small, let's say group of users and providers. So we had to rely also through this methodology, and let's say working, we were able with small numbers and still get statistically interesting results. And as you can see, an example of some of these statements around brands, like, for example, products developed by newcomers are trusted just as much as products from well-known producers, or around peer endorsement. Let's say users adopt a new product more likely if a colleague is recommending it. So in that way, we tested the kind of views of these users and producers. Most of them were actually quite experienced, I should also say, and that's also common in this field. Many of them actually more than 10 years of experience in both of these groups. And well, you could say that many of them were involved in some of the shipping activities in terms of the users, in tourism, in pilot services, in a consultancy, but also in icebreaking services. Many of them active in the European Arctic, but we also received, let's say, respondents from beyond, from Canada, from Alaska, and Yeah, and most of these users, yeah, you could say we're also used to using the automated services that are increasingly coming up. That was also an interesting, let's say, factor we wanted to test. Let's say overall, and that's of course what you were waiting for, what was the outcome, right? Or let's say overall we saw that there's actually quite a strong consensus of all kinds of factors that build trust. That kind of means that the users and providers agree on what is important and how the uptake of services can be improved. So there is actually let's say quite a common understanding of what is important and what is needed across providers and users, and this is mostly around issues like producer reputation, around trial periods, around peer recommendation, around the co-production, which is something that we did in this project. User-friendly design, etc. So on all of these issues, there was a consensus across the whole group. Another way of showing that is by calculating the kind of distance, let's say, doing that, and seeing also in this picture that actually most of the answers, let's say, given are pretty. Are pretty closely connected. I mean, you could say in this figure here that you see that the users are slightly more to the bottom of the graph. That kind of means that there were slightly more outliers there than there were in the provider and in the producer scape. But overall, there was a very strong consensus, as you can see. And that also shows in some of the graphs. I would like to actually pick out, let's say, 2 cases where this was not so much the case, because that is the most interesting thing. First of all, around paying for services, there was no agreement among the 2 groups. So the statement here is most users are willing or able to pay for high quality products. There was no consensus on this, let's say overall. But there was consensus in the user group on this, so they agreed. Whereas, let's say overall, the 2 groups disagreed, and this is interesting in the sense that this kind of idea really came out that users, they are willing to pay for high quality products and things that make a difference in their decision making, right? While this was not the case for actually providers, they don't believe that, so to say, or not as much. And secondly, and that's also really important and really interesting, I think, that around the comprehensibility, and this is of course also a topic for the future. Here, the statement was a new product is more likely to be adopted by users if it discloses underlying uncertainties. Like reliability estimates and capabilities. This is, of course, a new trend that is coming in all kinds of services, that users are informed about probabilities of a certain event happening. And while there was overall, agreement in consensus, actually the users, they disagreed with this. And you can understand this in different ways. Like providers might be, they might be very eager to make sure that these new products are will become part of the portfolio. Users do not maybe understand yet what this means, right? And what showing these uncertainties means for them. So whether this will be really useful or whether they will be able to interpret these results. So this was an important finding for us. Overall, and I'm reaching the end here. We also saw, let's say overall, that actually products from public entities are trusted more. They often users have a longer relationship with these products than with a commercial, let's say products. Also, that this idea of co-production is really important. So if users are part of the production of a service, this helps a lot. And that also users, they likely to trust products when recommended by peers, and that was also a key outcome of our survey. but that still, of course, quality remains key, and that there's also still, according to users, let's say there is work to be done there, particularly on accuracy, on the higher resolutions and higher frequencies of receiving services. I think I'll leave this there. And just to be talking about several next steps that are part of our research. So on the basis of this, we are also developing an agent-based model in which we are trying to, and this is in the context of a new project, of the Focus project, where we are trying to understand how these different factors together let's say, influence the uptake. So we've done kind of a static analysis, you would say, but now we want to see how these factors, let's say, interplay in taking up forecasts in a particular context. And in conclusion there, so there is a wealth of knowledge available to bridge this last mile, is what I want to say. So a lot is already known. Users and producers seem to largely agree about most of the factors that play a role here. And key factors that really come out here are producer reputation. So who is the provider? Also trial periods, also peer recommendations, user-friendly designs, etc. So we know quite a lot about what is important. That's the message. But also co-production approaches. So involving users in the production of these services seems to be really key. I'd like to leave it there. So thanks a lot. If you want to have more information about this, the paper that I'm basically, let's say, presenting on is published already. There is more information of the project available on the website. And thanks a lot for your attention. And maybe there are questions.
Yes, is it on? I think we have time for one question from the audience. Yeah.
Thank you for your presentation. I'm wondering, I didn't hear you talk about trying to control for the value of the decision. And I'm wondering if you consider that trust isn't binary. And so our risk taking might be different depending on the value of the cargo or our perception of what's at risk. And or do you think that your findings were universally applicable?
I do see what you mean. In the serious gaming approach, we did do that, because in this gaming approach you are able to play with such factors, like how much interest is involved. We also did that in the basis of how much value is involved in taking a certain decision, and then you see that plays a role in indeed the amount of risk that a user is willing to take with a particular, let's say, information available. In this survey, I don't recall it was part, but I could have another look. Maybe I forgot one or two of these of these statements. But it's true that plays an important role indeed.
Great. Yeah. Thank you very much. I would like to now welcome our next speaker. That's Justina Wojcicko. She is currently the head of the forecasting division at the Meteorological Institute here in Tromsø. She's worked as a meteorologist for just over 10 years, and she's also worked with professional meteorology as well. And today she'll be talking about the Arctic hurricanes. That's exciting.
Thank you very much, William. Okay, I will take you now on a very, very short trip to the weather forecaster world. And I will try to raise your awareness of the lack of marine, atmospheric, and oceanic observations. So, let's start. The world's ocean has been divided in 21 areas called Met areas to provide maritime safety information for shipping. Met Norway is responsible for the European sector, Met Area 19, of the worldwide Met Ocean Information and Warning Service. We provide maritime safety information in the form of marine forecast and warning products, including sea ice information. So, I have a question to you. have you ever heard about the Arctic hurricane? Not my colleagues from Met. You can raise your hand. Okay, good. Because the Arctic hurricanes are the polar lows. Polar lows is a beautiful picture, by the way, image, but it's scary. Polar lows are small but fairly intense lows that develop during the cold air episodes, outbreaks, during the winter season in the marine Arctic. They are generally smaller than ordinary synoptic lows, speed of propagation 15 till 25 knots, fastest recorded was 50 knots. And during the polar low episodes, you may expect rapid changes in the wind force, heavy showers of snow or hail, really be as a visibility less than 100 meters, high waves, icing on ships, and there is a really high risk of damage to the coastal fishing fleet and other smaller vessels. So, we have forecasters working 24/7, 365 days. So why it is so difficult to forecast polar lows? Well, we should start in the beginning with the numerical weather prediction. A numerical weather prediction uses mathematical models of the atmosphere and ocean to predict the weather based on current weather conditions. I will be back to this definition. So we need to talk a little bit and short about the modern uncertainty. There are several challenges related to the weather conditions in the high north, such as polar lows, processes close to the sea ice edge, and rapid changes in climate due to the global change. So, I will use a case from 25th of December 2022, so not so far. And I would like to present challenges connected to the polar low forecasting. As you see in the figure to the right, we use two weather forecasting models with 2.5 kilometer resolution to predict when and where the polar low will hit. And as you are able to see, the predictions are not similar. They place the low pressure centers differently, so the question is, for a forecaster, which one to choose. A tenth of kilometer is all it takes for a forecast to be perceived as wrong and put property and lives in danger. It is also essential to mention that the present state of the atmosphere is calculated from the comprehensive set of observational data from the entire global domain. So, back to our case, 25th of December. We are using observations as our forecasting, using observation, as you see to the left side, to check the accuracy of the numerical weather predictions model. But as you see in both figures, there is a massive lack of observations. Different times, this upstairs, some synoptic observations from 3 UTC, this on the bottom, satellite observation at 8 UTC. Different time, different observations, unfortunately, rarely at the same time, the same data. If you try to compare with everything, still it's difficult to know which one prediction is good to choose. So, we still, a little bit about polar lows in the changing climate, we still do not get a clear picture of how the changing climate will affect the polar lows. That's why we need to be prepared for all outcomes. So, there is a lack of observation, and how can we predict the future when we don't have a good overview over the present? So, there are approximately 11,000 stations on land making observations, 1,300 upper air stations. We use marine observation, aircraft-based observations, satellites, and weather radar observations. But I would like to move your focus to the contest between the density of observations at subarctic latitudes and to that of the Arctic. It is challenging to get observations. We do not have a lot of ships, we do not have a lot of airplanes or as many permanent observation stations in the Arctic due to logistic, expenses, and other difficulties. These figures really show the difference in observation coverage. Of course, we have our station on Bear Island and Hope Island, but it's not enough. So, why do we need more observations? Well, different types of observations contribute to better numerical weather predictions models. More observation will provide better quality weather and climate services. Our forecasters will get a better insight into a current weather situation and improved starting point for the weather forecast. More observation will increase forecast accuracy and in the end reduce forecast errors. And as you see to the left side, it is a circle, and this most important circle with I as a weather forecaster and the head of the forecasting division to talk about. Everything is connected with each other. You have researchers, you have operations, and users. That's why that is really important to have to get all these components into the weather forecastings with feedbacks from the users and observations with pre-processing, model calculating, post-processing, interpretation and communications. Our users will get a really good product, and again, when they will give us a feedback, we can develop it and improve it. So, what about the Arctic? We already heard that anticipated less sea ice volume will open up more opportunities for shipping in the Arctic. And ships are collecting a huge amount of weather observations. We have different programs. So, for example, the VOS, Voluntary Observing Ship Scheme, which is an international program that recruits ships to take, record, and transmit marine meteorological and oceanographic observation while at sea. But the new opportunity is coming now. Maritime autonomous surface ships. The International Maritime Organization works on the International Code of Safety to Maritime Autonomous Surface Ship, which we call for MAS code. MAS will be able to collect a massive amount of weather data, and we need access to this information. I checked the draft of the MAS code, this document, and guess how many places in that document meteorological and oceanographical observation are mentioned. Any answer? None. What with allowing access to this information? None. So, I think that you may feel really confused right now because I started with the polar laws, model uncertainty, lack of observation, and now the maritime autonomous surface ships. I got only 10 minutes and I met a huge shortcuts to present you how the weather forecaster world looks like. So I hope that this will be just a start for further discussion and hope that we will receive more observation. So, everything I talk about today has a common word, is access to observation. Accurate weather prediction deliver economics, environmental, and social benefits. Good data are the foundation of good decision. And the future is now. We are talking about the future, but future is happening now. The IMO and WMO are cooperating on maritime safety to different programs and projects, but we need to press, especially to the IMO, to include the weather and oceanographic observations component into the resolutions and other documents. So I will show you just a short video about the role of weather forecaster in the maritime forecasting.
When ships go to sea, they encounter many dangers, from collisions, rocks, and wrecks to all types of weather. In fact, over 30% of shipping accidents are caused by the weather. Maritime Safety Information and the Worldwide Met Ocean Information and Warning Service help to keep ships and people safe from harm. Since the sinking of the Titanic, which gave rise to the International Convention for Safety of Life at Sea, or SOLAS, the IMO, IHO, and WMO have been working to make shipping safer by coordinating the provision of warnings to ships in line with the Joint Manual on Maritime Safety Information. WMO has also created regulations and guidance for meteorologists to ensure accurate information reaches ships at the appropriate time. With ships constantly on the move, it's critical that weather information and warnings match their changing location and environment. To achieve this in the open waters, which are not governed by particular countries, the world's oceans are divided into 21 Met areas. The meteorologist on duty at the designated issuing service within each Met area is responsible for sending out regular forecasts and issuing warnings and advisories when needed to highlight dangerous weather conditions in that particular area. For coastal waters, national meteorological services are responsible for issuing marine forecasts and warnings. Let's take a look at how it works. Before sailing, a ship's captain asks for the latest forecast. She receives a warning of fog, a collision, and 2 drifting ships to be avoided. As the ship clears a narrow strait into shallower waters, a gale warning is issued by the meteorologist. Sailing through the Southwest Pacific on its way to Antarctica, the ship receives a warning of an intensifying tropical cyclone within the area. Storm force winds and dangerous seas with very high swells and waves lie ahead. Alerted to the danger, the captain changes course and steers well away from the tropical cyclone. Crossing the Antarctic Circle into the Antarctic coastal area, an ice information broadcast provides details of drifting ice and icebergs, periodic rain and snow, and warnings of freezing spray. For a while, all is quiet as the ship sails past numerous fishing vessels, until the captain receives an urgent warning of an erupting volcano and a drifting ash cloud, which could reduce visibility, damage equipment and engines, and lead to health issues. She makes sure she sails around it. Finally nearing her port of call, the captain is happy to receive a clear weather forecast. Thanking the meteorologist for all the information and warnings, she is grateful for another safe and successful voyage at sea. Maritime Safety Information and the worldwide Met Ocean Information and Warning Service keep ships and people safe.
Yes, thank you very much.
Okay. Due to time constraints, I think we'll move on to the next speaker. Our next speaker is Dr. Dina Abdelfatah, and she is from the Department of Technology and Safety at the Arctic University of Norway, and she's based in Harstad. And today she'll be talking about sea ice spray on boats. So welcome.
Well, thank you, Justina, for the perfect introduction. So my name is Dina Abdelfatah, and I am a professor of interdisciplinary things. I work on ice, I work on social science, I work on computer science, so it's really hard to put a title. But today I'll be looking at one project that we have going on at the moment with UIT, SINTEF, and also MET. And this will take a deep dive into how we can actually use crowdsourced information and other types of information to better understand a hazard that we are seeing more and more in the Arctic and other places around the world. Spray icing. So what is it? It is ice accumulation on vessels or other marine-based infrastructure. And that sounds okay from a starting point, but it actually can pose a major risk to marine activities in the Arctic in particular, because it can cause things like vessel instability, loss of economic revenue, and also loss of life. So it's not just the ice that's the problem, but what happens afterwards when it causes these issues on important structures. And why are we then having this as a topic? Why do we have a research project working on this? And why is there actually a demand for it? Because it meets a scientific issue alongside a societal issue as well. It's very difficult to predict spray icing because of the chaotic nature of what happens when it does occur. There's a lot of different parameters that have to go into play for this to actually happen. It's not just freezing of water, but there's a lot of different variables. And we have been having information, obviously, in the past. We have records that we can base things off of, but climate change is really starting to create this new challenge. So how do we then, again, as Justina said, how do we look forward if we don't have enough information in the now? And this is something that we need then for more recent and frequently updated data to meet that demand for prediction. So what we're looking to in the project is to try to crowdsource observations. We're trying to see if we can get weather observations, spray icing incidents, and also information on accidents or even near misses, so that we can then create better sea spray icing forecasts that are then grounded in these crowdsourced observations. And this benefit is that we can actually interact then with users. We can interact with real people that are facing these challenges. So we're also creating this link between science and society to better understand what is actually happening when these incidents do occur. And it also allows us to create a community of stakeholders that can then also tell us about the usability of our science and the information that is collected. So as we heard in the keynote speaker, this is something that we're seeing more and more as a demand for information in the years to come. And currently, there's also this issue of usability. So I'm just loving that, being the third speaker, and people have already talked about these things, that I can kind of ride that wave. But there is currently an issue of, you are on a boat, you want to provide information, and you have a form like this to fill out, for example. It has a lot of great information that we need, but it doesn't have that usability, and it's time consuming, and it requires things, for example, like trying to convert from UTC to local time. So there's a bit of a gap in both usability and kind of the applicability to try to collect information. So what we're trying to offer is something easier, hopefully more intuitive, and allowing people to kind of work with what they have. Right now we have an app that we're trying to create this new module, and I'll discuss more about the existing app. But what we're proposing is to have kind of this easy to use form with drop-down menus. It automates what we can, so it gets the position from the vessel, from the boat. It sets the reporting time on itself, so people don't have to then do this behind the scenes conversions and stuff, and they can just say, we have an issue, here you go, and the app can collect that information. And as I said, it's already trying to be integrated with an existing system, so that way you don't have to then download one more thing onto your phone or onto your device. So where we can kind of ride what's already going and what people are using, it's a lot easier than trying to create a new kind of thing that people then have to learn about and to use and so forth. So we're hoping then the existing community will support what we're trying to do. So this existing app is formerly called Fiskinfo, and now it's been renamed to Tilhavs. But it's basically a platform that's used largely with the Norwegian fishing fleet, and it's been around since 2013. So we've had a long history of them. The fishing fleet uses it to share information, also about not just the environment that they're working in, but also about their catch and other stuff. So it's kind of a comprehensive tool that fits a lot of different needs. And we then think working with this as our grounding app will give us a large user base for us to get information for our information. So we've been working on gathering user requirements and having stakeholder consultations thus far. And right now we're in this phase 2 and phase 3 where we're actually getting out the soft launch of what we've been working on to the Fiskinfo and Tilhavs community. So I think it's kind of nice to see that things are actually moving forward. We've been having a lot of, success is a really huge word and one we would like to use, but at least we're getting a lot of, support for what we're trying to do, and it's been moving forward. And in the future, we're going to try to also expand it to other things, as I will talk about shortly with the Barents Watch and so forth. So something that we, as I mentioned, are looking to collect information on incidents that are happening, but we also then want to support with spray icing incidents. So I'll also put a plug that one of my colleagues, Eric, is in the audience, who's actually working on these forecasts. So if you have more technical questions, talk to him afterwards. But we're trying to then update the forecast so that they can actually be used. And we're trying to also put this into an existing user base, which is Barents Watch. So this is something that we're trying to help people, for example, route plan, get more information about what's going on so that they can also have a better pathway without taking those decisions all on their own. So again, for the forecast, we're also trying to get an understanding of what we can do, how we can support not just getting the information out there, but in what format and in what way. So we've been having a lot of workshops thus far with stakeholders and people that need this information to discuss how they would like to see it and use it. So to end a bit on kind of now the interdisciplinary part, there's a lot of science and computer science and technical conversations that are being underway with this research project. But really the essence of what we're talking about, and kind of refers back to the question that we heard after the keynote speaker, is that what is the decision context that we're trying to support? What are the values of these decisions? What are we trying to do? And it's not going to just be the physical modeling that we have to look into. We actually have to look at the whole framework of what is the situation at hand and what do people need to do and for what. So that's also a bit what's interesting about this project being interdisciplinary. We have an opportunity to delve into this part of the decision process, not just why do you use this information, but what is it actually used for and what will it help you do if you do or do not have it. So my part of the project then is to really try to understand the spray icing decision making. Who are the stakeholders? We talk about this term a lot, like what actually does that mean in terms of the user groups and the people that we're referencing? We have to start to peel the onion a little bit more to kind of understand at what point does which person have an invested interest in this kind of information. And what are the decisions that they do? For example, when they do have a spray icing incident that they're faced with, is it a go or no go on land, or is it actually they're out at sea and having to figure out whether they turn back or turn on the heaters? So there's a lot of different decisions that people in these situations have to face. So this is where then the information needs become really important, both from the user side, but also from the producer side for us in the scientific community. So lastly, the path forward is we actually really want to, not create this in a black box and work only with this really small and important, but small niche of people working on spray icing. I think as we see I've already seen from the conversations thus far in this room, there's a lot of commonalities and different things that are happening. So how can we leverage that knowledge from different products, from different communities, to also make sure that what we're doing is applying that and moving it forward as a whole community? So we're not only interested in creating this viable end product, but also to create a process that amplifies users and producers' needs and information. So I hope that, we can have this as be a starting point for, many interesting discussions. We have maybe time for one question, and if not, here's my email. I'll be happy to hear from you later on. Thanks.
We do have time for one question. Does anyone have any? Okay, I have a question. It's more of a practical question, sort of climate change type question. Are you seeing more sea spray icing events as time is going on, or is this just sort of a horizontal trend as time is going on?
Yes, and I think this is probably a better posed question for my colleague Eric, but we are seeing for sure that it is something that is continuing, and we will see for further more events. But how long that will occur for is a much broader question that I cannot answer easily.
Okay.
I can answer.
Yeah.
Yeah, we had an article in 2018 where we looked at the trends in spray icing, and we saw that it was actually more events in March, but less events in December. So there is some seasonal shifts in spray icing. So we don't know how it will continue in the future.
Okay, great. Thank you, Dina. So our next speaker today is Isolde Glissena. She is from Bristol University. She's currently undertaking her PhD, and she is looking at sea ice thickness changes from satellite altimetry and the Canadian ice charts. So welcome.
Thank you. Thank you. Today I would like to present my work on creating a proxy product for sea ice thickness in the Canadian Arctic. So normally when we measure large-scale sea ice thickness, we use satellite altimetry. And these satellites measure the surface height, and from that we can estimate sea ice thickness. However, polar-focused altimetry missions only go back to the early 2000s, with ISAT and MVSAT being launched in 2003. And that gives us a bit of a short record to really study long-term trends and variability. And also, these products don't work really well in the channels of the Canadian Arctic, because there are not enough leads to calibrate the satellite, and also there's a bit of contamination from the land that interferes with the signal. So this is where the ice charts come in. So I'm working with ice charts from the Canadian ice surface. These are quite interesting because they contain really a lot of information. So next to sea ice concentration, they also contain information on stage of development, and they have 14 different classes of stage of development, leading from new ice all the way up to multi-year ice. And they also contain information about form of ice, which you can see as the flow size. And also within one of the polygons, or within each of the polygons, there can be up to 3 different classes of ice. So they contain a lot of information, and then they've been created since the 1960s, but they've been getting a lot more reliable since 1996 with the launch of RadarSat. But what these ice charts do not contain is sea ice thickness. Okay, so here's a quick look into the ice charts. On the left, you can see some information from the ice chart in November 2018. So on the top, you can see the stage of development. With the redder, the older the ice is. And on the bottom, you can see the form of ice or the flow size. With the redder, the larger the flows are. And when we compare that to sea ice thickness, so on the right is sea ice thickness observations from CRYSAT-2 from the same month and year. And you can see that there's a large overlap in the spatial pattern, and that there's definitely a relation between the information in the ice charts and the sea ice thickness. So what I'm doing is using this relation between the information in the ice charts and sea ice thickness to create a proxy product for sea ice thickness. So what I do is create a machine learning model, or more specifically a random forest regression, that uses information from the ice charts and then estimates sea ice thickness, both further back in time than we have observations, and in locations where we can't use the satellite altimeters, like the channels in the Canadian Arctic. And so we train this model on CRYSAT-2 observations that we have had since 2010. Okay, so how does the model do? So first, we've compared the model to CRYSAT-2 observations themselves. So what we have done here is trained the model on every year except for one winter. So we left out the data from 2017 to 2018 in the training data set, and then we trained the model. So on the left, you can see November 2017, with on the top the outcome of the machine learning model. So that's what we estimate the sea ice thickness would be based on the ice charts. And then in the second row is observations from CRYSAT-2. So that's the observed sea ice thickness. And we can see that there is a large correlation. The model does really well in this month. It captures the thicker sea ice thickness north of the archipelago. It captures this thicker band of sea ice thickness going along the Beaufort Gyre. It also captures slightly thicker sea ice in the west of Baffin Bay than in the east. So it does a really good job here. And then on the right, we've done the same for April in the same winter. And here we can see that it still captures the thicker ice north of the archipelago, but there are some locations where the model deviates a bit from the observations. One of those locations is right here, near Point Barrow on the coast of Alaska. And we think this might have to do with the sea ice being pushed up against the coast, dynamically thickening, forming ridges, and that's what the model doesn't capture because there's no dynamic thickening in the ice chart. So it's still first-year ice, but it's been dynamically thickened. So that's where the model doesn't do a really good job. We've done the same for every year. So for every year that we have CRYSAT-2 observations, we've trained the model, left 1 year out, and then compared it to the observations from that year. And that's plotted on the right here in the scatter plot. And if you look very closely, if you look very closely to this line, you can see a black dotted line, which is the one-on-one line, but you can also see a dashed blue line, which is the trend line through the dots, and you can see that they overlap very closely. So on average, the model does a really good job. However, there are definitely some locations where it deviates, so it goes up to a meter different from the CRISAT-2 observations, which can be due to multiple reasons. It can be due to this dynamic thickening that I mentioned, but it could also be due to more variability in CRISAT-2. So for example, this observation from CRISAT-2, I personally don't believe it's that thick. So that's where the model can also deviate. And so we get the model with an uncertainty of 30 to 50 centimeters, depending on the month of the year. Okay, and so next to just validating against CRISAT-2 itself, which is what the model's trained on, so that's not the best source of validation, we've also validated against multiple independent data sets. And I'm only going to discuss one here because of time. So here we validated the model against fast ice measurements in the Canadian Arctic archipelago. So in orange, you can see the outcome of the model, and in blue, you can see the observations from the stakes. And why is this one really interesting? It's because it's a validation data set that we have in the channels where we don't have the CRISAT-2 observations. And we can see that it does a really good job. It captures the observation within an error of 20 centimeters, which is less than the model uncertainty. So that's really good here. Okay, and then this is the product that we get. So after we've trained the model, we've applied it to every ice chart that we have since 1996. And then you can get a 25-year-long record of sea ice thickness from November till April. And this is the first time that we can really capture sea ice thickness in the channels without having to interpolate or anything. And it's also the first time that we really go back before 2003. And then we can look into trends and variability. I'll go through this a bit quickly, unfortunately, because of time. But this is the trends that we can get from this record for April sea ice thickness. So you can see some locations of thinning, most notably in the north of the Baffin Bay. Yeah, so there's a lot more information in here, but I'll skip over that quickly. And so lastly, I'm currently working on trying to make this product operational because these ice charts are released every week within 1 or 2 days after the observations are done. And then we can theoretically immediately apply the model and get a sea ice thickness for that ice chart. So this is an example where I've applied it to the most recent ice chart when I had to submit the presentation. So yeah, that's what I'm working on right now, but that will take a while, a few months to get going. So get in touch if you want any updates or talk to me later. Yeah, thank you.
Okay, thank you. We don't have time for questions, but if you do have questions, we could take them after, just during the panel discussion. Okay, thank you, Isolde. Now I'd like to welcome Dr. Jack Landy. He's an associate professor in remote sensing, and he's part of the surfer group at the university here in Tromsø. Welcome.
Thank you, William. Fantastic, and I have to thank Isolde too for giving an introduction to CRISAT-2 data, which is what I'm going to be talking about as well. So, as William said, I'm part of the surfer group at UIT. One of the main goals of our group is to develop new sea ice data products from spaceborne sensors that are really useful for monitoring and forecasting sea ice in the Arctic Ocean. And today I'm going to be talking about one of those projects where we are trying to develop a year-round sea ice thickness record from the ESA radar altimeter mission, CRISAT-2, and then a little bit about how we're starting to use those to make forecasts of sea ice in the Arctic Ocean. So what's the premise for this work? Well, CRISAT-2 was launched in 2010, and since then it's been providing us with these fantastic observations of the sea ice thickening during winter months, the increase in volume over winter. And that's what I'm showing here is one of the data sets that estimates the sea ice thickness. What's also really obvious, though, from this animation is we have these gray areas in the summer months. So as yet, when the sea ice starts to melt and we get ponds forming at the surface, researchers have had a tough time converting these Cryosat-2 observations into valid sea ice thickness estimates. And it turns out that one of the key requirements of an upcoming EU mission called Crystal, which is basically a follow-on mission for Cryosat-2 set to launch in 2028, is to provide meaningful sea ice thickness estimates during the summer months. So as part of this project, we wanted to work out with Cryosat-2 data whether this goal is actually realistic. So what's happening in the summer months? Well, in winter, we've got this cold, dry snow cover overlying our sea ice. And so we typically get diffuse scattering contributions of our Cryosat-2 radar from across the Cryosat-2 footprint. And this produces these broad echoes, like you can see on the right here, with these long trailing edges. But in summer, the snow and the ice begins to melt. It pools into these melt ponds. And these typically provide a really strong, coherent reflection of the radar. And that often comes from the melt pond that lies closest to the nadir point, the central point of the Cryosat-2 footprint. And that typically produces these strong, peaky, specular type echoes. In the winter, these broad sea ice echoes are readily distinguishable from those that we get from leads, where the ice cracks and moves apart, and we can measure the height of the ocean. But in summer, these peaky echoes from melt pond-covered sea ice appear to be indistinguishable from leads. So my colleagues and I, from a variety of different institutions in different countries, we've been working together for quite some time now, longer than I'd like to admit, to try to overcome some of these challenges associated with the processing in the summer. And I'm going to talk about these very quickly, and if you're more interested in the methods, please check out our 2 papers here. But the first major thing that we had to do was to accurately detect the leads in the melting sea ice in summer. And we did this by developing a training data set for machine learning. So we identified local variations in Cryosat-2 parameters for leads, flows, and what we call noisy flows, where we get a variable response. We did this from SAR images that were within 15 minutes of a Cryosat-2 overpass, so the 2 satellites were coincident. We then used a portion of this data set for training a 1D convolutional neural network. And this could identify the locations of leads to an accuracy of 90%. So that's great, step 1. Step 2 was that these melt ponds also cause a bias in the range measurement of our radar. So they typically bias the height of the freeboard, the portion of the ice that sits above the ocean surface, low. So we get too thin freeboards. So what we did was we performed thousands of numerical simulations of the Cryosat-2 radar waveform, like you can see on the right here, for various sea ice surface roughness and melt pond coverage scenarios. And from these simulations, we were then able to create a theoretical correction that could be applied onto the Cryosat-2 freeboard measurement. The next step is to convert from this radar freeboard, this Cryosat-2 radar freeboard, the portion that sits above sea level, into an estimate of sea ice thickness. And we did this by taking our corrected radar freeboards. We have to account for the propagation, the penetration of the Ku band Cryosat-2 radar into snow that sits on top of the ice. There's still snow on the ice at the beginning and the end of the summer melt season in the Arctic. We use snow depth and density estimates from a Lagrangian snow evolution scheme, snow model LG. And then we just simply estimated the ice density based on the ice type, which is consistent with the winter processing. So what do we get? When we solve this equation, we get our estimates of the sea ice thickness here. And this is going from a kind of conventional winter processing scheme from March and April in 2016 through to our summer processing scheme as the ice begins to melt up to August. And I'll skip over the validation just in the interest of time, but you can, if you're interested in this, you can find out more in our papers. So then, once we've performed these new methods for the summer months, we can stitch together our ice thickness record for the winter and the summer into a consistent time series without these gaps. And what we can do is then use this time series to investigate things that we just haven't been able to in the past when we've had gaps in the summer. So, for example, we can look at sea ice thickness anomalies where the ice is much thicker or much thinner than it normally is in a specific location, and we can follow and track those anomalies over time to see if they persist. Do they go from the winter into the summer and then back into the winter again? Is there any correlation between the ice thickness and the ice area? So that's what we did, and that's what I'm showing here. This is a bit of a complicated plot, but I'll try and guide you through it. So we created a sea ice volume data set from our ice thickness data from Cryosat-2. We then calculated the correlation coefficients between the ice volume measured at a lead time on the y-axis here, up here, and then we calculated this against the sea ice extent at a target day on the x-axis here. In the center here, this is the same thing when we use sea ice extent at a pan-Arctic scale to forecast future sea ice extent. And the stippling, these dots here, just show where one is doing better than the other, and the colors are just the correlations. So what we can see is that at very short lead times of up to a few weeks, the ice extent does a really good job of forecasting future ice extent, but then the ice thickness really takes over. And here I've plotted the correlations for September, and we can see that using the ice thickness data extends the forecast skill of these seasonal forecasts by several months compared to just using ice concentration, ice extent data. So of course, then instantly what we're thinking about is if we use these ice thickness data in and assimilate them into a numerical sea ice and ocean model, can we make better forecasts of future ice extent? And that's what we're starting to do. This is work led by Yongfei Zhang and Mitch Bushuk from GFDL at NOAA in the US. What they've been doing is they've been assimilating ice concentration, sea surface temperature, and the ice thickness data into a coupled ice and ocean model. And these are the initial conditions of the sea ice volume anomalies that we get when they do this. So in black is the Cryosat-2 data. In blue is the initial conditions when just assimilating SST and ice concentration, and then in red is when the ice thickness data is included as well. We can then take these initial conditions and perturb different things within the model, for example, the albedo, the strength, and the snow conductivity schemes within the sea ice module, to create ensemble predictions that then evolve over time, and we can use these to make probabilistic forecasts of future ice extent. And just my final slide here, these are some of our early reforecasting experiments when we do this. So what you're seeing here is the anomaly correlation coefficient between these model predictions at a certain point in time, at a lead time, forecasting September sea ice extent. And if you just look at the difference between the red and the blue here, we see that our forecasts when assimilating the new summer ice thickness data can extend these skillful forecasts by a few months of September sea ice, and that's great. So just to summarize, ESA's Cryosat-2 mission was launched back in 2010, but all these challenges associated with melt ponds have prevented researchers from being able to produce summer ice thickness data. But luckily, we were supported through a variety of generous funding sources, and I had a fantastic group of colleagues to work with to try and overcome some of these challenges to produce a first decade-long gap-free ice thickness record, which is available publicly at the BAS Polar Data Center here. And this is now giving us new opportunities to assimilate these data into dynamical ice and ocean models. And then by assimilating the observations, we can make probabilistic forecasts of future ice area on a seasonal basis. And one of the things that we're thinking about now is trying to produce these data in near real time. This is what I'm really interested in for the next couple of years. Hopefully it takes less time than that. But if we can produce these data in near real time for the summer, this would then be really useful for improving maritime operations and safety and forecasts. Okay, thank you.
Okay, thank you, Jack. And we're going to have to move on, I'm afraid. You'll get time for questions at the end. So our final speaker, that's Truls Karlsson. I think he's the only speaker actually from Tromsø. He's doing his PhD at the university here. He's also part of the Surfer Group, and he's working on SAR imagery and sea ice analysis.
Thank you, William. I'm actually not from Tromsø, I'm from Vesterålen, but so I'm going to talk about combining C and L-band SAR data for sea ice monitoring. So why are we interested in sea ice monitoring? Sea ice monitoring is used for operational ice charting, which you can see an example of on the right, as well as for climate studies. And the main workhorse for sea ice monitoring is SAR data, synthetic aperture radar, particularly Sentinel-1, as this is freely available. So why do we want to use SAR? As SAR is a radar, it's independent of solar illumination and weather, so really suited for the high Arctic. It also has a high resolution compared to something like passive microwave, but it can be difficult to visually interpret. So on the left here, you can see an optical image, which looks sort of like you would expect. You can see snow and ice and open water. While on the right, for me at least, it's not really intuitive what I'm looking at. This is a SAR image of sea ice. But there are a lot more features and structures apparent in the image compared to the optical image. So what determines how the sea ice appears in a SAR image is both the SAR parameters, such as frequency, polarization, incidence angles, and spatial resolution, but also the sea ice parameters, for instance, surface roughness, volume structure, temperature and salinity, and the snow cover. For snow cover, particularly, the moisture content is important. So the top figure here shows some of these interactions between the radar signal and sea ice, while in the bottom you can see sea ice at different roughness scales, as well as some thin ice and an open lead. Right, so why do we want to combine C and L band, and what is C and L band? C and L band denotes two radar frequencies. L band is a longer wavelength than C band, and we want to combine them because they provide complementary information. L band in particular is penetrates deeper into the ice and can also penetrate snow cover better than C band, while we have a long time series of C band data dating back to the 90s, so we have a good understanding of how the sea ice appear in these images. As they have different are different wavelengths, they are sensitive to roughness at different scales from the ice. And the main difficulty in combining C and L band is that there are currently no satellites operating at both frequencies at the same time, so we need overlapping images from different sensors, which can be a challenge. So this here gives an illustration of how different ice types appears in both C and L band for different ice types. Yeah, sorry. These are some classification results using both C and L band separately, but also combining the two. So if you look here, you can see a ridge structure, which is very apparent in the L band image, but hardly visible in C band. So by combining the two, you are able to pick up on this ridge. And this is something that L band is very well suited for. Oh, sorry. Yeah, this is another example. In L band, this whole region is classified as young ice, while C band is able to pick up that there is actually some very thin ice or even a lead. So by combining the two, you get a more complete picture. And this shows the benefit of combining the two frequencies. So this is what I'm currently working on. an area on the northeast coast of Greenland referred to as Belgica Bank. Currently, I'm working on the landfast ice, simply for making the overlapping easier. This is the blue box, approximately. The reason I'm working on this area is because of the SIRFA cruise, which took place in spring 2022. So a lot of field data and drone images were collected here, as well as CNL band SAR data being tasked specifically for this mission. We have both quad-pol data and ScanSAR images. So quad-pol has 4 channels, polarization channels, and a very high resolution, but a small coverage compared to ScanSAR data, which is what's being used operationally. So this red box is the outline of a ScanSAR image, while the little green box is the quad-pol image. You can see examples on the right of this. These are some preliminary results. This is an unsupervised classification, and this gives an indication of the separability of different classes in your data set. Here I've used 3 classes on both CNL band separately as well as combining the 2. So for C band, it's basically 2 classes and a little bit of the 3rd class on the left there. L band, there's a more even distribution, and particularly these features are well separated, but there's a lot of noise, particularly in this region. But when we combine the 2, it's they're more clearly distinct, and features are separated better. So going forward, we are going to continue to investigate the separability of different ice types using a combination of C and L band. We're going to explore scattering mechanisms, particularly with the quad-pol data, in combination with the in situ data collected during the SIRFA cruise. And we want to look at time series of data, as we now have a lot of both C and L band available over this area. So there's a lot of interest in the topic of combining C and L band, as there are several L band missions upcoming, such as ALOS-4, NISAR, and ROSE-L. And there are also some more upcoming C band missions, Sentinel-1 C and D, and Sentinel-1 Next Generation. So lastly, I would like to acknowledge the data providers, and thank you for your time.
Thank you, Truls from Vesterålen. Yeah. Great. We have about 15 minutes remaining, so I would like to ask all the speakers to come up onto the stage, and we will have a short panel discussion. Also, if you had any questions that you didn't get the opportunity to ask, we can do that at the very beginning, just to get some things, the ball rolling. So, does anybody have any questions for any of the speakers to start with? Yes.
Hello, thank you for your presentation, and thank you for provided the nice product and profit model. So I would like to introduce myself briefly. I'm a PhD candidate at Norwegian University of Science and Technology. I'm also an emerging leader of this program. So I focus on the shipping safety in the Arctic. I have interviewed many captains and also developed models. We found that the ice ridges is the most hazardous factor for the ship navigating in the Arctic. So from your model, from your product, but I don't know, I haven't seen how will you deal with the thickness of the ice ridge. Because I think the last speaker, you have identified the deformed ice, but I guess maybe you just use the surface roughness to identify this is the deformed ice. But for a ship operator, we focus on how will you estimate thickness of the ice ridge. This is because the ice ridge on the top is called a snail, and the water is called a keel. Yeah, so I think under the water, the keel is much bigger than the surface. So my question is, how will you estimate the thickness of the ice ridge? Thank you.
Who would like to answer that question?
So all your models consider the ice ridge.
Pass it down to Jack.
Yes. Yeah, it's a good question and a very difficult question to answer from a remote sensing basis. So we can use in situ measurements to investigate ridges. People use upward-looking sonar on moorings, for example, to look at the draft, the depth of a keel. That's a very good way of doing it, but then those measurements are spatially sparse, right? So to do it from remote sensing, we're indebted to new technologies, and I think that NASA launched a mission called ISAT-2 a few years ago in 2018. And ISAT-2 is an altimeter mission like Isolde and myself were talking about, but it's a very high-resolution laser altimeter mission, and it is capable of resolving specific ridges. So people in the US now are starting to develop data products on the roughness and the height of individual ridges along these profiles that are measured by the laser altimeter. So if you want to, I can point you towards some of those new products from NASA.
Great.
We have one question from our online participants. It is addressed to Ms. Glisenar. So Alexei Buni is asking, if the model is trained on ice charts, what is the output resolution, spatial and temporal, of the sea thickness product? Do you plan adding any other features to minimize RMSE?
Yes, that's a good question. So the ice charts don't really have a resolution. They're polygons. So the size of the polygons is kind of the resolution. But it's trained on Cryosat-2 sea ice thickness, which I'm using a 50 by 50 kilometer product. So what I showed here was 50 by 50 kilometers spatially. The ice charts are released weekly, the ones that I'm using. But for the product for sea ice thickness in the past, I'm making it monthly, so I'm taking multiple ice charts and I'm combining them. But if I do it operationally, I would do it weekly because there's an ice chart every week and there's no reason to wait until I do it. And then there was a second question about integrating more data, I think, and that's something I skipped over here because 8 minutes is tight. But I'm actually also including scatterometer backscatter into the model, which helps bringing the root mean square error down a lot, if that answers the question online.
Yeah. Great. So I'm going to ask a question that could probably be its own conference itself. What do you foresee are some of the biggest obstacles we currently have when we are trying to take all of these great products that are being produced and all this amazing research that's being done? What are the obstacles of getting that into operations? Because it seems to be that there is a huge amount of work being done, but very little actually filters through into operational products.
I can give it a start. So I'm now trying to make my product operational. And the reason I can do that is because I got some seed grant funding and because my labor is very cheap because I'm a PhD student. But in a few months, I'll be done with my PhD and I don't know what I'm doing after. So who knows what will happen to the product? So I guess money and continuancy is quite difficult.
Yeah. I think funding is always something to talk about. Anyone else have a comment on this? Justina?
As a weather forecaster and the head of the division, I think that's the most, one thing which is important here, that the implementation and operating, make the products operational, it's important to include this phase of this phase into the project in this very beginning of the when researchers and developers are planning their project. They should talk to us and they should include implementation into the project, and then maybe we will be able to have more money and funding to start to use this project, because I see that we have a lot of really good products, a lot of really good projects, which in the end are landing on the side somewhere. So maybe this is some solution.
Great.
And maybe to also shake it up a bit, but do we even need it as a product? Do we actually have to produce this if we want to have it be used by people? That question I don't think we ask enough, and it also is something that we will have to consider more under both tighter budgets and also societal demands. In a prior life, before I was working in this field, I was in the international development world, and we saw time and time again people would go out like, oh, there's an app that you can use here in Uganda to track floods. And people just didn't want it. And we were surprised in the software world, why were people not using this great piece of information? Because it didn't meet a need that they actually wanted. So I think this goes back to, the question of demand and people working together and making sure that this user-centric design is really at the heart of what we do.
Yeah, like to answer that question, I think it's important to realize that that often there are still, let's say, disconnections between different departments, of course. And I mean, of course, we are mostly looking at users versus services, but that goes for the whole value chain, for the whole production chain. So there could be really interesting research, being done also on the basis of what I have showed regarding, let's say, ideas or let's say consensus between different departments of a MET institution, to see how much aligned these groups actually are around some of these issues. That could be really interesting in that regard. But I also agree with you. Like the proof is in the eating, right, of the pudding, or something like that. They always say, right? So it's ultimately users decide what they use, and like another thing that could help though is in another project is that we are also, and that's also what I heard you say, let's say working with all kinds of. Because we talk about users, providers, but in a way, let's say everybody is a user, everybody is a provider at the same time. So this world is much more blurry, and there's all kinds of actors and platforms and e-navigation systems in which these products could be delivered. Let's say much more directly as part of a much more integrated system to users, and this might also play a really important role in the next years.
Great response. Any more? Quick one from Jack.
Am I allowed to? It was a very big question, William. So
it's a huge question.
Big answers. Something just then to add. I was fascinated with these survey results that you showed, especially this lack of consensus over whether users thought they would want to pay for products, because I think in the public sector world, in university world, we're always dealing with short-term projects. It's either soft money and people working on postdocs, or it's PhD students who have a finite time. And if the users are not willing to pay for these products, then it means we can't maintain them and they'll die. But does that mean that the market's not there? They don't really need them? Because if they're not willing to pay for them, do they really need them?
Well, it was actually the other way around. They are willing to pay. So there is a market. So actually the idea was that there is more market than providers think in this area, and that's also something. So that was the outcome of that result. But it's also that I think that in the coming years, there's all kinds of developments also around the sustainability of shipping. That is changing, in which actually these services will become much more important to reduce fuel, to to stimulate, let's say, investments in more sustainable ships. So all kinds of information services and reporting services will become more important for other, so not only the actual shipping company, but also for investors in ships, for example. They want to know what is on board and what is available and what can be used. So that will become, I think, much more important.
Great. That's a great answer. We have a question at the back first.
Please wait for the microphone because we have online participants.
Okay. So hi everybody, I'm Sampo Vihreilehto with ABB Marine and Ports, and I was part of Marcia Lammer's Salient Seas project back in the day. So my question is, your project is moving on this sort of boundary, if you will, between the public, the university or the education level, but also the private companies. We have many companies providing these ICE services. We have universities studying them. And for me, this has been the question that how did you feel sort of, what was the response from the private companies when you started, asking people to come in, join the captains, the service providers? Because I see it that maybe perhaps some companies might see it that you're perhaps on their turf and, the departure from university to the business side. So how did you find it?
Yeah, I mean, that is an issue. Like if you work with some users, you might be biased, right, towards some users. But that in a way is also, it's unavoidable in co-production. You have to start somewhere and make a choice for working with some actors, some users at some point. But it's also important to remain open in such a process. So that's also what we did. So if we met, let's say, other users that were interested, we also took them along in these exercises and in these advisory processes. This sort of openness, I think, is important. Sometimes we are already very happy, right, that there are certain users that are willing to commit to such projects. Overall, I think we can't complain really. We really felt that also in your case, but also in the case of other actors. There is really a strong interest from the sectors in this, and I think you might also have something to say.
We have 1 minute. I will give you 1 minute.
Okay. Yeah, I think there is definitely, this is going to be a big question, I think, both for the scientific community, for society, and for private companies moving forward, is who gets to decide and how, and who has the final say in these kind of questions. So I think there may be instances where it just doesn't maybe is necessary. If the private company has what they have and it's working for them, maybe that's enough. But maybe in other cases, like the market question that you were saying, maybe there is a market, we just have to shift and find that market. So having that openness is a great way to look at it, but also for the scientific community to also be a little bit more willing to listen, that maybe this is not the door to go into if it's actually shut and not working. So, yeah, thanks.
Okay, great. We are out of time. There were some more questions. You will have time over the lunch period. We will probably stay in the room for a little bit as well, just to have a little bit of discussion. Otherwise, thank you very much for joining today. Thank you to all our speakers who presented. I think we had some really good views on gaps and observations and user and producer relationships. So we will have an area sectioned off in the lunchroom if you have lunch tickets where you can come and discuss things with our speakers or together. Otherwise, thank you very much for joining today.